Okay, so today we're going to continue our discussion on square roots and how to work with square roots. And the specific topic that we're going to look at today is something called simplifying radicals. And all a radical is, it's another word for saying a square root. So what is a radical? A radical is a square root. So when we talk about simplifying radical expressions, what we mean is simplifying expressions that have square roots in them. And then the square root symbol we call the radicand. So for example, if you had something like the square root of 4, how you would more properly speak it or read it is as radical 4. So we're going to look at some samples, and we're going to start really, really basic. So starting with number 1. If I have the square root of 4, I'm pretty much just going to go to my calculator. The square root of 4 is 2, unless I know it, which hopefully some of these we do. The square root of 256 is 16. The square root of 324 is 18. So pretty basic so far. When you get into these fraction problems, you pretty much just want to split the fraction up. You want to take a look at the square root of the top number separately from the square root of the bottom number. So split it up into two smaller problems that are easier to manage. So for this, the square root of 64 over 81 is going to break up into the square root of 64 over the square root of 81. And then we know the square root of 64 is 8, and the square root of 81 is 9. So the whole thing would reduce to 8 over 9. Same thing with this one. The square root of 9 over 100 would reduce to the square root of 9 over the square root of 100. We know the square root of 9 is 3, and we know the square root of 100 is 10, so the whole thing reduces to the square to 3 over 10. All right, so I did 1, 3, 5, 7, and 9. I would like you to do 2, 4, 6, 8, and 10 as part of your homework. One of the things that you're going to find makes this work easier is if you have some of those perfect squares memorized. So we're going to quickly take a minute here and write out those common perfect square numbers. And I'm going to start with 0. So 0 squared is 0. And going backwards, the square root of 0 is just 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. And 10 squared is 100. So if you can recognize these more quickly, the work becomes easier. But I'm going to challenge you to go further than that. Instead of just memorizing the first 10 perfect squares, I'm going to challenge you to memorize the first 20, because 11 squared, 12 squared, 13 squared, all the way up through about 16 squared are pretty commonly seen in Algebra 1 problems. So going beyond this, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, 15 squared is 225, 16 squared is 256, 17 squared is 289, 18 squared is 324, 19 squared is 361, and 20 squared is 4 400. If you can memorize those, your job becomes much easier. Now, one of the reasons why it's important to memorize these is because a lot of times we are going to be dealing with problems that aren't perfect squares. But just because they're not perfect squares does not mean there's something that we can do. And what I want you to avoid doing is just going to your calculator and getting a decimal, because that's not what this is about. We are no longer relying on our calculator. We are no longer looking for a decimal. Instead, we are doing something called simplifying non-perfect square root radicals. So really what this means, another way that you'll see the directions for these kinds of problems, we are writing the answer in reduced radical form instead of decimals. So instead of just going to your calculator and getting a decimal answer, we are writing it in reduced radical form, which is something you are going to have to do a lot in geometry, so be ready. The basic idea behind getting a radical expression into reduced radical form is that you want to take the number and you want to break it down into factors, and you want to try to find these perfect squares hidden among the factors. So for example, and it helps a lot of times if you do a quick factor tree. So 24 breaks down into 4 times 6. So what that means is I can rewrite the square root of 24 as the square root of 4 times 6. Now, there's a rule with these roots and these radicals that if you have a multiplication under the root, you can separate it into two separate roots, the exact same way we did with these fractions, because after all, this fraction is just division. So when you have multiplication or division under a root, you can separate it into two separate roots, which means this can turn into the square root of 4 times the square root of 6. Now we know 4 is a perfect square. We can see it right there. The square root of 4 is 2. So this part of it is going to reduce to 2. 6 is not a perfect square, so there's nothing we can do with this except leave it under the radical. So reducing the square root of 24, it reduces down to 2 root 6. So that's what you want to do. You want to take a number, you want to break it down into its factors, and you want to try to find these perfect squares hidden among the factors. And if there's more than one perfect square, you are looking for the biggest perfect square. So when I take a problem like 72 here, doing a quick factor tree, the first thing I notice about 72 is that it's even. So I'm going to go ahead and divide 72 by 2, and that gives me 36. So 72 breaks down into 2 and 36, and I can see right away 36 is one of my perfect squares. So that means I can rewrite the square root of 72 as the square root of 36 times 2, which I can then separate into two roots, the square root of 36 times the square root of 2. And then we know the square root of 36 is 6. Can't take the square root of 2, so your final answer is 6 root 2. Okay, I did 11 and 13 for you. I would like you to do 12 and 14 for homework. When you're ready, please flip it over to the back. We're going to look at 2 more examples. Okay, for number 15. 15 breaks down into 25 times 7. So just like we did with the problems before, 175 can be rewritten as 25 times 7, and then I can break that apart into two roots, the square root of 25 times the square root of 7. We know the square root of 25 is 5. The square root of 7 does not reduce, so my final answer is 5 root 7. Okay. I did 15. I want you to do 16, 17, 18, 19, 20, 21, 22, and 23 for your homework, and then I'm going to do 24 for you. All right, so 450. The first thing I see about 450 is that it's divisible by 2. And then what I can see here is 225 is a perfect square. The square root is 15. So this would turn into 225 times 2, split it apart into 2 separate roots. But I want to take a look at another way of doing this problem. What happens if you don't find the biggest perfect square when you're trying to break it down? So over on the side, I'm going to do this again. The square root of 450. Maybe instead of factoring out a 2 first, maybe you said, ooh, this is divisible by 5. So let's factor out a 5. 450 divided by 5 is 90. 90 breaks up into 9 times 10, and I like that because 9 is a perfect square. And then 10 breaks up into 2 times 5. So maybe you would be inclined to then say, okay, 9's a perfect square, so I'll do 9 times, and then putting these numbers back together, 5 times 2 is 10, times 5 is 50. And you would say, oh, well, here's my answer. Square root of 9 times the square root of 50 is 3 root 50. The problem with that is there's another perfect square hiding in 50. 50 can break up into 2 times 25. And the square root of 25 is 5. So really this would turn into 3 times 5 times the square root of 2, which would still get you back to the same answer. So remember, you're not just looking for any perfect square. You want to find the biggest perfect square, and you want to keep factoring until you've gotten all the perfect squares outside of the radical. Okay, so in summary, down here, things you want to remember. Radical is another name for a square root. Some of the more common perfect squares we listed out on the front. It's a good idea to memorize the first 20 perfect squares. And to simplify non-perfect square roots, you are trying to find the biggest perfect square hiding in the factors, and you're going to pull the root of that outside of the root, and any leftover numbers are going to stay under the root. Okay, now we need to talk about one more thing. So I want you to look at your homework sheet. Everything that we've talked about so far has just been numbers. So what on earth do we do when we have a problem like number 11 on the 10-1 skills practice side? How do I do something that's got letters? And the basic premise is still the same. So zooming in a little bit. You're still going to want to break this apart. Because remember, 81c squared d to the 4th is the same thing as 81 times c squared times d to the 4th. And when you have multiplication, you can break it apart into separate roots. So this can break apart into the square root of 81 times the square root of c squared times the square root of d to the 4th. The square root of 81 is 9. That part's done. When you have letters and you want to take the square root, you're going to divide the exponent in half. So the square root of c squared is just c. The square root of d to the fourth is d squared. So that's not too bad, but this was easy because my exponents were both even. I could divide the exponent in half. Now we need to look at number 13 to see what happens when I can't divide the exponent in half. What you want to do is you want to find the biggest even number to pull out, and then the leftover is going to stay under the root. So 75 is going to break down into 25 times 3. So splitting this apart, I'm going to have the square root of 25 times the square root of 3 times m to the fifth. The biggest even number that I can get to that's less than 5 is 4. So I'm going to take m to the fifth and I'm going to split it up into m to the fourth times m. And then n squared, 2 is an even number, so I can leave it as n squared. Then I can say, okay, square root of 25 is 5. The square root, I can't take the square root of 3, so that's going to stay as root 3. The square root of m to the fourth, cut the exponent in half, is m squared. Can't take the square root of m, so it stays under the root. The square root of n squared, cut the n exponent in half, is n. Then, writing it in a more standard and acceptable form, you're going to take all of the pieces outside the root and put it together. So 5 m squared n, and then you're going to take the pieces that are left under the root and you're going to put it back together under one root. 3m. Okay. With number 15 and number 16, it's going to start off just like what we did on the last note sheet. But the problem is, when you go to split this up, the square root of 1 over the square root of 6, the square root of 1 is 1. That's pretty easy. The problem is, there is no square root of 6. It's a decimal, so it would have to stay as square root of 6. However, some math person came along one time and said, you know what, I don't like roots in the bottom of fractions. I can't leave it there. I need to get it out of the root. So how I do that then is by whatever root is on the bottom. You are going to multiply the top and the bottom by that root. Because here's what's going to happen. 1 times root 6 is root 6. Root 6 times root 6, you can put those together and that becomes the square root of 36. And the square root of 36 is 6. So the final answer is root 6 over 6. You are not done until you no longer have roots in the bottom. And you're going to have something similar with number 16. So the first thing you're going to want to do with number 16 is you're going to want to take these two and put them together under one root. This is going to turn into 6 over 7 times 1 over 3. And remember, when you multiply fractions, you go straight across. Top times top. 6 times 1 is 6, all over. Bottom times bottom. 7 times 3 is 21. And then that reduces to 2 over 7. And then, just like with number 15, I'm going to split that up to take the square root of the top all over the square root of the bottom. But again, you can't leave a root in the bottom. So I'm going to multiply my top and my bottom by whatever root is in the bottom. My top, root 2 times root 7, turns into root 14. All over root 7 times root 7 is root 49. And we know the square root of 49 is 7. So your final answer is the square root of 14 all over 7. Okay. One last thing we need to talk about, and then we'll be done. Take a look at number 21. I said with 15 and 16, you can't leave a root in the bottom. The problem is, how on earth do you get rid of it when it's written like this? And what you have to do is you have to multiply by what we call the conjugate. You have to multiply the top and bottom by the conjugate of the bottom, which is going to look just like the bottom, only you have flipped the sign in the center. So the conjugate of 4 plus root 5 is 4 minus root 5. So you're going to multiply the top and bottom by 4 minus root 5. And I'm going to go ahead and put this in parentheses because it's going to be easier to see how to do this. When you go to multiply your top, you're going to just take this number and you're going to distribute it. So it will turn into 8 minus 2 root 5. When you go to multiply the bottom, you need to FOIL it out. Now here's why you multiply the conjugate, because this should look very similar. This should look like that special pattern that's going to give you a difference of 2 perfect squares. So when I FOIL this out, first terms, 4 times 4 is 16. Outer terms, 4 times negative root 5 is negative 4 root 5. Inner terms, root 5 times 4 is positive 4 root 5. And my last terms, root 5 times negative root 5 is negative root 25. And then what you'll notice here is these two cancel each other out. So you're left with 16 minus the square root of 25. And we know that the square root of 25 is just 5. So 16 minus 5 is 11. My final answer is 8 minus 2 root 5 all over 11. You're going to do the same thing for number 23, but what I want you to notice here is here in 21, my conjugate had a minus. Well, in 22, you start with a minus. So your conjugate would have a plus. So you'd want to multiply your top and bottom by 2 plus root 3. And then distributing the 3, you would get 6 plus 3 root 3 on the top, all over. Foiling out the bottom, you would get 4 plus 2 root 3 minus 2 root 3 minus root 9. The 2 root 3 and the negative 2 root 3 cancel each other out. Root 9 is 3, so 4 minus square root of 9 is 4 minus 3, which is just 1. So this over 1 is just 6 plus 3 root 3. Okay, that's it. The problems that I've not done are your homework, and that will be due Monday. Have a fantastic weekend.